Hello everyone, my name is Fernanda. I'm a PhD candidate from the University of Vieira, and I will show a part of my doctoral research that involved the production of new polymeric materials from lignin. So let's move on. Here the outline. I will introduce the research context, the methodology used in this work, the main results, and the last one, the concluding remarks. Okay. Lignin is a natural polymer, is a natural polyol that can be from trees, that can be isolated from black liquor, a byproduct of craft process. And this isolated lignin can be converted in a liquid polyol to be used to produce bio-based polyurethane products such as foams and adhesives with a wide range of applications, for example, construction and automotive industry. And today I will present the use of responsive surface methodology, a tool of design experiment, DOE, to optimize the oxyalkylation of lignin to afford polyols with good quality. Isolated lignin is solid in powder form, and the most used process to liquefy lignin in liquid polyol is the use of oxyalkylation with the propylene oxide, called oxypropylation. However, this propylene oxide has some features, for example, low boiling point, which makes the process need to be carried out at pressurized medium with a higher temperature, so present a risk to our safety. How to solve this problem? One alternative to propylene oxide can be the use of cyclic carbonates, for example, propylene carbonate PC. This PC, differently to propylene oxide, has a higher boiling point, which allows that process can be carried out at atmospheric pressure, even with a higher temperature, ensuring the safety process. So at the same time, we are developing a bio-based product, and we should look at the quality of these bio-based polyols. And speaking about quality parameter of them, polyols, hydroxyl number and viscosity are the key parameter in the polyurethane formulation that has a great impact on the polyurethane formulation balance and also the final quality of these polyurethane products. So, some questions arise here. For example, can we produce this lignin-based polyol with the same quality as conventional polyol? Or do you have opportunity to reduce the cost process these polyols? Let's see. First of all, I want to show how the oxyalkylation of lignin with the PC works. Basically, lignin has hydroxyl groups, phenolic and aliphatic ones, that can be converted in oxyalkylated groups. For example, aliphatic ones can react with the PC, leading to carbonate linkage, while phenolic ones can react with PC, leading to polyether polyols. In the literature, there are few studies discussing the oxyalkylation of lignin with 6 cyclic carbonates, and especially discussing the effect of process variables on the quality parameter this lignin-based polyol. In fact, those work discussed more the effect of process variables on the chemical modification, the efficiency of conversion, and not the quality of this polyol, namely hydroxyl number and viscosity. So that's why in this work we decided to optimize the oxyalkylation of lignin using a craft lignin isolated by lignin-boost process with a different amount of PC, different temperature, and different times. And the catalyst used in this reaction was a basic catalyst DBU. And of course, the quality parameter evaluated here was viscosity and hydroxyl number. So let's see the DOE methodology. So responsive surface methodology is a methodology which allows us to understand how and what the process variable affects the responses. Where the most used design is a factorial design, for example, full factorial design. And the first step starts with the selection of process variables and the response. And in our case, we decided to investigate the effect of PC amount, temperature, and time on the hydroxyl number and viscosity. So regarding the ranges, consider they were based on in literature and also in lab experience. For example, PC amount start minimum for equivalent molar to maximum 10, temperature minimum 170 to maximum 200 Celsius degree, and time minimum 1.5 hours to maximum 3.5 hours. So varying these variables on 3 levels gave us these 27 experiments. And the second step starts with the data analysis. Let's move on. So the data from that 27 experiments were analyzed by the least square method that gave us these second-order equations to determine the predicted values for hydroxyl number and for viscosity. So the quality fitted model was evaluated by ANOVA, by plots of experimental values versus predicted values, and also the residuals of predicted values and the Pareto chart. But here I will show just the main results. Continue. So here we have the plots of experimental versus predicted values for both a hydroxyl number and viscosity, and the difference between them, predicted values and experimental values, are relatively small. Looking the R square, the coefficient of determination, for both are greater than 90, so indicating this regression is significant. Also, you have here the Pareto chart. The Pareto chart indicates for us which effects are statistically significant on the responses. And in this work, all linear terms are the most significant, followed by quadratic effects. Especially PC amount, the PC amount is the most significant on the model, on the responses. So let's move on. So from 3D plots, we can see how you can see the interaction between process variable and how they affect the responses. Let's see what we found for hydroxyl number. So the plot A, we have the interaction between temperature and the time. And we can observe as temperature and time increase, the hydroxyl number increased as well. So in the red surface, we have higher values for hydroxyl number, and in blue surface, we have low values for hydroxyl number. Looking at plot B, we have the interaction between time and PC amount, and you can observe as the time increases, the hydroxyl number increases as well. But PC amount is not does not significant effect here. So it means the surface don't change significant as PC amount change. And the same tendency was observed in plot C. So PC amount does not significant effect, but you have just the effect temperature here. So as temperature increase, the hydroxyl number increase. So let's move on. On the other hand, the viscosity, the PC amount, has significant effect on the viscosity. So you can see in the plot B and C, the viscosity values are low in almost all range. But you can see the tendency is as PC amount decrease, the viscosity increase. In general, the tendency is higher temperature, long timers, and low amount of PC, higher values for viscosity can be obtained. So, and looking here, the interaction between temperature and time, we have higher values for viscosity if the process carried out at higher temperature and longer times. So let's move on. And the next step involves the validation of fitted model. For that, 3 additional experiments were carried out using different conditions, and the experimental values for hydroxyl number and viscosity are consistent consistent with the predicted values. Since then, they are within the confidence interval of models, so in the blue line here. So what is this? These results indicate for us that the models are reliable and the models can be used to optimize the process. Let's move on. So this lignin-based polyol will be used to produce rigid foams and also these polyurethanes. And of course, they are different products. They have different required values for hydroxyl number and viscosity as well. So the defined targets for both are based on commercial polyols, common values of commercial polyols. For example, hydroxyl number start from 90 to maximum 600 milligram KOD per gram, and the viscosity 0 to 30 Pascal per second. And in this work, the software that we use has a future prediction profile, you can see here, that allow us to see how the response, multi-response change as we change the process simultaneously, and also has this desirability function associated. So for those who don't know, in process optimization with multi-response, the desirability function is the most used method that allows the simultaneous optimization of two or more responses. Basically, we have these models from second order equation, and these second order equations can be converted to into individual desirability function, where the values range of the desirability function range between 0 to 1, where the 0 is associated with unacceptable quality and 1 is associated with the best quality. And in this work, to obtain a process with a high desirability, it means to achieve this target, the process should be carried out at this condition. So temperature between 180 to 185 Celsius degree, time 1.8 to 2.5 hours, and PC amount between 5 to 7 equivalent molar. Work in this condition is possible to reduce PC amount from 30 to maximum 50% and increase lignin content from 12.5 to maximum 25%. So let's move on. Okay, now the optimization to polyols that will be used to produce adhesives. And of course, the defined targets are different. So hydroxyl number start with 90 to maximum 308 milligram KOG per gram, and the viscosity 0 to 10 Pascal per second. So to obtain a process with high desirability here, the process should be carried out at this condition. So temperature between 170 to 175 Celsius degree, time between 1.5 to 2.5 hours, and the PC amount between 5.5 to 7.5 equivalent molar. So work in this condition is possible to reduce PC amount maximum 45% and increase lignin content to maximum 22.5%. Okay, so last one, the concluding remarks about this work. So we can improve the process, the oxyalkylation of lignin using a DOE, and also specifically for this work, you can see that the viscosity is highly influenced by PC amount, and hydroxyl number is the most influenced by reaction time. And also we reach out our objective, it means we reduce the PC amount and also increase the renewable content on the final product. And the last one, you can reduce the PC amount around 50% depending temperature and the reaction time using the oxyalkylation process. So I finish here. Thank you all for the attention.
Good morning. it is a pleasure to be here to talk with you about integrated forest biorefineries, and I would like to start by sharing with you some facts. Lignosulfonates were one of the first dispersants added as an admixture to concrete and have been used since the 30s as plasticizers or water reducers. The commercial production of aniline from lignin present in spent sulfite liquid started in North America in 1937. In Sweden, during the Second World War, sulfite mills produced ethanol to be used instead of oil. And the first craft lignin extraction plant was started up in 1942 in US. In 1975, the first per kilo plant was built in Finland. 10,000 tons per year of per kilo protein was produced from spent sulfite liquor, and the second plant started in 1981. The recovery of furfural and acetic acid from spent sulfite liquor evaporators condensated started in 1983 in Austria, and the first xylose recovery plant from spent sulfite liquor was introduced in 1995 in US, and the second plant, located in Austria, started in 1997. It's clear that biorefinery concept is not new to the pulp and paper industry, special for the sulfite pulping process, even before the first known definition of biorefinery appeared. Today, when you look at industrial scale biorefineries, acid sulfite pulping has a larger product portfolio when compared to the craft process. We have bioethanol, xylose, acetic acid, furfural, lignosulfonates, and vanillin being produced at sulfite pulp mills and using well-proven technologies. And so, acid sulfite process has exclusive features for serving the biorefinery industry as a source of raw materials for bioproducts. The purpose of today's presentation is precisely to review biorefinery pathways and technologies for COIMBRA mill. COIMBRA is the only pulp mill in the world that produces a dissolving pulp from Eucalyptoglobulus using a magnesium-based acid sulfite process and a TCF bleaching. COIMBRA produces 120,000 tons per year of dissolving pulp and sells about 55,000 tons per year of lignosulfonates. The major components of COIMBRA spent sulfite liquor are lignosulfonates and sugars. As you can see, xylose is the main sugar, comprising about 66% of the total sugars in the thin liquor. Therefore, COIMBRA's biorefinery concept could be based on xylose. COIMBRA combines unique features, the acid sulfite process and the use of Eucalyptoglobulus, which gives it technical advantages regarding xylose valorization. Xylose can be converted into furfural, xylitol, or sold as pure xylose. Starting with xylose. Xylose is one of the most versatile sugars with a wide range of applications. At industrial level, xylose is mainly extracted from lignocellulosic material by acidic hydrolysis in standalone plants. But xylose is also extracted from spent sulfite liquor in two existing sulfite pulp mills. According to the specialized literature, xylose separation from spent sulfite liquor can be carried out by continuous countercurrent chromatography in the form of ion exchange simulating moving bed. And also based on the literature, namely patents, we can also sketch the process block diagram, identify the main unit operations, and estimate for COIMBRA a production between 7,000 to 9,000 tons per year of pure xylose. Let's look now at xylitol. Xylitol is a sugar alcohol with no petrochemical alternative and with applications in pharmaceutical and food industries. It is one of the top 12 value-added chemicals from biomass released by US Department of Energy in 2004. Since the early 70s, the use of xylitol in dental health has been widely studied and recognized. Xylitol can inhibit the growth of several bacteria, which prevents ear and upper respiratory infections. And because it has almost the same sweetness as sucrose, but lower energy and lower glycemic index, it has been used as a sugar substitute. At an industrial level, xylitol is produced by chemical hydrogenation of pure xylose in the presence of a catalyst at elevated temperature and pressure, followed by xylitol purification. For COIMBRA, we estimated a production between 6,700 to 8,600 tons per year of xylitol. Furfural. Furfural is the only organic molecule produced at industrial scale that is universally obtained from biomass. Industrially, furfural can be produced by acid hydrolysis and dehydration of pentoses contained in lignocellulosic biomass, or by liquid-liquid extraction of spent sulfite liquor evaporated condensate using high boiling point solvents. Currently, there is no commercial plant producing furfural from spent sulfite liquor, but in the specialized literature, some references can be found. Basically, we have a first step for sugar conversion into furfural at high temperature and low pH, followed by furfural purification that can be accomplished by distillation. It's consensual that the fast removal of furfural from the liquid phase during the dehydration of the pentoses is essential in the mitigation of side reactions that result in low furfural yields. For COIMBRA, we estimated a production between 4,100 to 5,300 tons per year of furfural. In conclusion, the chemical characterization of spent sulfite liquor from COIMBRA mill allowed to see its potential for some promising biorefinery products. The main components are lignosulfonates and sugars, and the main sugar is xylose because the raw material is eucalyptoglobulus. Xylose can be converted into furfural, xylitol, or sold as pure xylose. Based on specialized literature and for each of these new products, it was possible to sketch the process block diagram, identify main unit operations, know the typical ranges for the overall yields, and estimate their annual production in a biorefinery context. And the main conclusion is that COIMBRA combines unique features: the acid sulfite process and the use of eucalyptoglobulus, which gives it technical advantages regarding xylose valorization. And that brings us to the end of the presentation. Thank you.
Good afternoon, my name is Patrícia and I'll be presenting the work entitled Cationization of Eucalyptus Kraft Lignin, Preparation and Properties. Lignin is the second most abundant biopolymer on Earth, and together with cellulose and hemicellulose is one of the three main components of the plant cell wall. However, lignin is still largely underutilized, in particular for materials. This is due to its complex, irregular structure that makes it very difficult to work with, and has disappointed quite some PhD students and even hardcore scientists. Since decades, lignin is separated from wood by several different pulping technologies. The amount of lignin solubilized into the pulping liquors accounts to about 100 million tons per year, but about 98% of these are used for energy production and recovery of processed chemicals. Among the pulping technologies, kraft pulping is today by far the most frequently applied technology. However, only about 1 per mile of the solubilized lignin is commercialized. In terms of soda pulping, the production numbers are rather marginal. And lignosulfonates still form the highest fraction of technical lignins commercialized, more than 1 million tons per year, even though sulfite pulping is on the retreat, with a current global production of 7 million tons compared to nearly 400 million tons of kraft pulp. So, a relatively high percentage of lignosulfonates, around 15%, are commercialized for several applications, from emulsifiers to dispersants to binders and adhesives to complex agents. So the question is, what renders lignosulfonates so attractive for materials application? It's mostly due to their excellent water solubility, which is imparted by the abundance of the polar sulfonic acid groups. This leads us directly to our goals of the project. imparting full pH scale water solubility to craft lignins, and to perform preliminary experiments to explore in how far the products can be used in traditional and novel applications. The source of this material used here was a typical black liquor from eucalyptus kraft pulping, which was subjected to lignin isolation and purification using the lignobus process. As evident from the low NaS sugar contents, our starting material had high purity, which can be very important for many material applications. The results of ultimated and functional groups analysis have been used to establish the C9 formula for these lignins, which corresponds to a C9 molecular weight of 211.4 grams per mole, and the phenolic group contents were 0.83, and the total hydroxyl groups, aliphatics and phenolics, were 1.47 units per ppm. Furthermore, the non-condensated fraction of the lignin structure was also characterized by means of nitrobenzene oxidation, revealing a low yield of phenolic aldehydes, which can be shown here, and a high syringyl-glycyl ratio of 3.8, which both are in agreement with literature. Shown here is the approach we were using to produce water-soluble kraft lignins. It's a relatively facile one that is conducted in alkaline solution at somewhat elevated temperature, using the cationic reagent 3-chloro-2-hydroxypropyl-3-methylammonium chloride, and in a first stage, CHP-TAC is converted to EP-TAC in alkaline solution, which then undergoes a SN2 epoxide ring opening reaction, which is triggered by the phenolate ions and which eventually affects the formation of ether linkages between lignin and the quaternary moieties. After a certain reaction time, the reaction mixture was neutralized and the product obtained was purified by dialysis prior to characterization or, if required, prior to application. Aiming to track down the most efficient reaction conditions, key parameters such as molar ratio of CHP-TAC to lignin, lignin concentration and sodium hydroxide concentration, reaction time and temperature were varied, and their impact on the product properties in terms of water solubility and degree of substitution were studied. So the degree of substitution was calculated using the formula shown here, where N is the nitrogen content, 211.4 is the molecular weight of the starting material, 14 is the atomic weight of the nitrogen, and 151.6 is the molecular weight of the EP-TAC. Variation of reaction parameters reveal that molar CHP-TAC to lignin ratios of at least 1 are required to afford products fully soluble at all pH. Besides molar ratio, the results also shown that time and temperature impact the degree of substitution. As example, for a CHP-TAC to lignin ratio of 1, extending the reaction time from 1 hour to 2 hours had a positive effect on the degree of substitution, as reflected by the 0.5 weight percentage gain. However, this effect started to level off when prolonging the reaction from 2 hours to 3 hours. Also, at elevated temperatures, we could see that this accelerates the introduction of quaternary ammonium moieties as demonstrated for CHP-TAC to lignin ratio of 2. So based on this, we could conclude that optimal conditions were CHP-TAC to lignin molar ratio of 1, 70 degrees Celsius, 3 hours, 1 weight % sodium hydroxide, and 10 weight % lignin content. The table on the left side shows selected results of ultimated analysis and instrumental analytical techniques. All products feature relatively narrow molecular weight distributions and relatively low molecular weight. And they had an excellent water solubility of more than 750 grams per liter. Zeta potential measurements conducted for the most promising material confirm a positive value that amounted to 15 millivolts. And the FTIR IR spectra confirmed the successful lignin at the example of the peak at 966, which was assigned to the methyl groups of the quaternary ammonium atom, and also by the decrease of the peak at 1220, which represents the CO stretching vibrations for phenolic OH groups. Further confirmation of lignin modification was accomplished by carbon-14 NMR spectroscopy. First, the significant change of the peak pattern is evident in the aromatic region. While for the unmodified lignin, the more pronounced peak in the range of 145 to 155 ppm is centered at around 147.9 ppm, which represents C3, C5 atoms in non-heterophyte guaiacyl and syringyl moieties. This peak pattern is reversed for the cationized products. Since the phenolic hydroxyl group is now heterophyte, as evident from the signal at 152.5 ppm. According to the signal intensity ratio of these two peaks, it was estimated that at least 70% of the free phenolic groups have reacted. The successful modification was also confirmed by the prominent new signal at 54.6, which has been assigned according to the literature to the methyl groups attached to the quaternary ammonium nitrogen atom. Thermogravimetric analysis revealed clear difference between the parent and cationized lignins. It's evident that even in nitrogen atmosphere, the cationized lignins are more sensitive towards temperatures beyond 200 degrees Celsius. This is mostly likely due to well-known thermal degradation of quaternary ammonium salts, which affords tertiary amines. Furthermore, alkenes can be formed by an E2-Hoffman elimination mechanism, which is due to the presence of a proton in beta position relatively to the ammonium nitrogen atom. Many quaternary ammonium salts are quite hygroscopic, therefore selected products were studied with regard to their water absorption characteristics. At the example of the rather dry and humid environment, the results reveal a relatively low hygroscopicity for the two products tested, since the maximum weight gain was around 8% after 4 days for 33% relative humidity, and the weight gain at a high degree of humidity was naturally higher, but level of about 50%. The water-soluble lignins were also characterized in terms of antioxidant activity. The method used relied in the first line on the ability of free phenolic groups, such as for radical trapping and reduction of activated states, so it was not surprising to see that antioxidant activities drop quite significantly with the introduction of the quaternary ammonium moieties, because phenolic OH groups are now heterophyte. However, it's still worth to mention that still some 10 to 15% of the original antioxidant activity is present for all the materials tested. The last results shown that the flocculation activity towards the anionic dye called Remazole brilliant blue. The results shown that up to 83% of the dye could be removed, and that each cationic lignin had an optimal dosage for maximum dye removal. Moreover, lignin with a degree of substitution of 1.2 was insofar interesting as it showed a phenomenon reported in the literature, which occurs when the concentration of the flocculant is higher than required. In that case, and also here, overcharging results in a restabilization of the dye particles and therefore in a reduced dye removal from the solid state. At the example of the eucalyptus craft ligno-boost lignin, it has been demonstrated that introduction of positively charged quaternary ammonium moieties is a facile approach to render craft lignin similarly well water-soluble like lignosulfonates. Broad gradations of the process has shown that key products characteristics, including molecular weight characteristics, degree of substitution, polarity, and therefore material properties, can be adjusted within a wide range depending on the target of application. Finally, cationic craftlink can be a relatively cheap component to impart a series of properties such as reinforcement, hydrophobicity, compatibility, UV protection, antimicrobial and antioxidant activity, as well polyelectrolyte interaction to composite materials. I would like to thank all colleagues that contributed to this work, as well, of course, all funding and collaborating institutions, including University of Aveiro, Raiz, and the Navigator Company for their support.
Boa tarde a todos. Good afternoon to you all. I hope you listen to me carefully, quite clear. From the image, I think not. Can you listen to me now? Okay. So first of all, thank you to everybody to listen to this section. A special thank to the speakers that share with us their work on these different fields. Now we will start the question and answer. Hope you listen to me. Okay, I will move anyway.
Olá.
So, first question for Fernanda. Says, what is the main challenge to use lignin in polymeric materials? Well, I don't think that, yeah.
Acho que agora já conseguimos ouvir.
Sim, eu estou a ouvir. Conseguem me ouvir?
Eu agora consigo, mas não ouvimos nada até agora.
Okay.
Pois.
So I will start again.
Thank
you now for listening. I'm glad that you can hear me now. I don't hear myself, so I hope my voice is quite pleasant to you, because as I tell you, I can't hear myself. So once again, thank you for being here. Thank you for the audience to be there. And now we will start the period for question and answers. And I will start with a question to Fernanda. And the question says, what is the main challenge to use lignin in polymeric materials?
I think the main challenge, the main limitation to use lignin on the moment on polymeric materials are the variable chemical composition, also the solubility of lignin on the other polymeric matrices, and also the high cost to produce this bio-based product compared to conventional product.
Okay.
That's it, I think.
Okay. So a question for Isabel says that is there any current effort at COIMBRA to produce xylitol and furfural from pulp fuels?
So at this point, we are doing a preliminary assessment of all the possibilities for COIMBRA, but at this stage is preliminary, and we are using or based mainly in patents and specialized literature. So we have a way to go until we conclude about the possible pathways for COIMBRA.
Okay, thank you. Another question. Can you tell, I think it's for Patrícia, can you tell how some molecular mass distributions were measured in this study?
Yes, so they were measured by size exclusion chromatography.
Okay.
Yeah, using a mobile phase of water, and it was measured by that. Yeah.
I have just another question. You talk about continuation of the eucalyptus, but is this after the reaction? Is the product stable, or the reaction can be reversed, and we may have problems with the product?
No, the product is quite stable, so it doesn't precipitate. Again, it stays in solution for a while. So I can say that I produced samples around October, and until now they still are in solution. So I don't see precipitates.
Okay, thank you. I have here a question that is more than is more a provocation, but okay, I will put the question to everybody. There is a myth of you can make everything with lignin except money. Is there any plan for separating lignin in navigated mills for further development? Tricky question.
So maybe I can say what it's been described in literature. So it's something that you can read in the literature about biorefinery, that it's a solution to a bottleneck on the lime kiln, that you can remove lignin, and that can help the process. In terms of the navigator, I might not be the best person to speak about it, but I think in this approach, it's well worth to remove lignin from the mill.
Okay. So
I can comment.
Okay, of course. Sorry.
I think it's possible in the next, I don't know, 5 years. I think Navigator has the potential to isolate lignin together. For example, company, I think it's possible in the next years.
Okay. Thank you. But anyway, I understand the question, because the final question is that when you are putting on the market a new product, you have to compete with something that is already there, unless it's a completely new product. So anytime you do some working, some research work, you have to be careful that you are competing with someone else that is already there. Okay. So that is the sense of the question. Thank you. I will pass to a new question. This is for Patrícia also. Sorry to say your name in English. This is for Patrícia. How they use the lignin? How they use the lignin as UV protector, as a binder to a resin, or use it as a coating?
How they use? So in the literature,
ultraviolet protector, UV protector.
So yes, so it's been described in the literature that lignin can be used, for example, as a sunscreen. This has been described, and it's described also how they use the lignin. So as a coating, this could be also very interesting. Yes, and it's possible. I don't understand how they use. What does it mean?
I think it's something related, if I see the question, to a sunscreen or something like that.
So you could use it in a formulation. So you could add it as a powder in and prepare a solution from it, or you can use it in a solution and do, for example, surface treatment with it.
Okay.
And this would. Yeah.
One question. I don't understand clearly the question, but I put it anyway. Is there some danger in using xylitol as sweetener for wastewater? Is for Isabel?
Well, I think that for humans, it's already well established. But for animals, there are some limitations. So I'm not sure if you are adding these sugars as a feed to the F1 treatment. I'm not sure. So I cannot. I don't know. I really
manual. So I just focus on the applications for human and for the food industry. That for sure, it's clear that have advantages. So, and it's already proven that it's healthy and safe to use.
Okay, I have a new question for Fernanda. I'm trying to go to all the questions that I'm getting here. And the question, sorry, let me check if you understand the question. Okay, you have shown in the work that there is a variation of the hydroxyl group and viscosity with temperature, but in the hydroxyl group, it was shown in the graphics, if I remember, that there is an increase and then a decrease. Can you explain why this happened?
So these hydroxyl values, wait, I will formulation this.
It's too much graphics.
Okay, wait a moment. You asked me how you can increase the hydroxyl number or decrease, okay?
Yes. Yes.
According to the process variables. Basically, these process variables, temperature, also timing, so it means help to accessibility to achieve the accessibility of the hydroxyl number of lignin, and in this reaction, lignin can be modified in oxalkylated groups. I don't know if it's clear or not.
Yes,
Basically,
I think so.
If you have high temperature or high time, a long time, sorry, the accessibility of hydroxyl numbers of lignin can be facilitated, and this help to convert lignin hydroxyl number in oxalkylated groups.
Okay, thank you for the answer. I have another question for Patrícia. How do you recover the cationic lignin after finishing the reaction?
So after finishing the reaction, it stays in a solution. Depending of the application, you can do a purification step or not. And then I normally freeze dry it, but you could use it as a solution of pH neutral.
Okay, thank you. Just checking for another question. Sorry, one moment, please. I'm waiting for our audience to put more questions. But in the meantime, I will ask a question to Isabel. On the presentation, you give some examples of end products which you wasn't. But can you give more information about the end products that can be made from furfural that are already in the market?
Yes, so the furfural, it's it can be used for lots of applications, and but the main application for furfural, it's to produce furfuryl alcohol. So this is like it represents 88% of the furfural conversion.
Okay. One question for sorry. No, sorry to interrupt you. Please proceed.
No, so and then you have these. You can produce resins.
Okay.
From the furfuryl alcohol.
One additional question to Fernanda. In your presentation, we see that viscosity increases very much for low values of PC concentration. Can you explain that, why that happened? Do you have an idea why this is so?
So can you repeat the question, please?
Yes, in the graphics of your work, we can see that viscosity increases a lot when the concentration of the polypropylene kernel is quite low. Do you have an explanation why this happened?
What is quite low? The PC amount?
When the concentration of PC is quite low, the viscosity increases a lot. Do you have an idea why this happened?
Basically, if you use a low amount of PC, because PC is reagent, and also at the same time, PC is solvent.
Okay.
If you use low amount of PC, you have a low solvent in this process, and the viscosity of lignin, this lignin-based polyol increase. But basically, because PC, the action of PC is reagent and solvent at the same time.
Okay, one last question for every one of you, and the question will be the same. When can we see commercial products made from your research? Okay, I will rephrase the question. When do you think about the future? When do you suppose we can see any commercial application based on the research you have done so far? Because that is the end of any research. Who starts?
So from my side, all the products. So it's probably this question is not for me, because what I discussed in the presentation, mainly things that are already there, and some of them are they start in the 30s or something. So for my presentation, all of the products are being or were produced or are being produced now. So they are already there.
So
It's a little bit. It's a little bit the same for me. So if we imagine that I have a water-soluble lignin, and like Isabel spoke, lignosulfonates are well used in a cement since decades. This is one of the potential applications. If we think about antimicrobial, antioxidant coatings, barriers, this is also something that it's well known these days. So. Actually, some of the applications that we could explore with this lignin are already in the market.
Okay. So, who is missing?
For my side, I think to put lignin-based polyol in the market at the moment, you have the big challenge regarding the cost, and also the quality of these bio-based products need to be comparative as conventional. And at the moment, you have this challenge to circumvent and the cost and the quality of these bio-based products.
Okay.
But I think in the next years you need working to circumvent this challenge, because the politicals and the climate change requires this bio-based product in the market.
Okay. I thank you for your last answer, especially because it was a very difficult question to answer. But anyway, thank you to you all. Good luck for you. And for the audience, thank you again for listening to this section. I hope you stay with us for the next one coming in a few minutes. And thank you very much, and good afternoon to you all. Thank you.
Thank you.
Thank you.
Thank you all.